Our next talk this morning is by Kevin Pratt.
Okay, thanks. So I'll be talking about some new applications of wearing rank or symmetric tensor rank to designing faster exponential time algorithms for some hard problems. So I'll start by introducing wearing rank, and I'll describe some sorts of problems that it can be used to characterize the complexity of. And as a real algorithmic example, I'll show how this perspective combined with known bounds on the wearing rank of some specific polynomials immediately yields some faster polynomial space algorithms for problems such as counting simple cycles of a given length in a graph. I'll then state the main sort of algorithmic theorem, which is an algorithm for approximately counting subgraphs of bounded tree width in some host graph. And this algorithm actually follows from an upper bound on some quantity I call a n comma d, which you might call the wearing support rank of the elementary symmetric polynomial. And it turns out that this quantity is very closely related to some previous methods in parameterized algorithms and gives a very precise generalization of them. So the wearing rank of a homogeneous degree d polynomial f is the minimum number r, so that f can be expressed as a sum of r dth powers of linear forms, just homogeneous degree 1 polynomials. So, for example, it can be checked that the monomial x1, x2, x3 can be written as the following linear combination of 4 cubes of linear forms. And of course, since we're working over the complex numbers, you can always absorb the coefficients outside the linear forms. So this shows that the wearing rank of this monomial is at most 4. Now it actually turns out that the wearing rank of this monomial is equal to 4, but proving that lower bound even is not a simple thing. And in general, saying anything about the wearing rank of a particular polynomial is a very hard problem. And it's not one that I'm going to focus on in this talk. So wearing rank has appeared in, it's been studied for quite a while in the context of classical algebraic geometry and invariant theory, going back to work of Sylvester in the 1850s. It's appeared in the context of algebraic complexity theory, of course, as a restricted circuit model, also in the context of geometric complexity theory and the exponent of matrix multiplication. And in the case that D equals 2, this is just the rank of a symmetric matrix. So you're actually all familiar with wearing rank, even if you didn't know it. So I'm interested in wearing rank in this talk in the context of the following problem. So say you have some linear functional on the vector space of homogeneous degree d polynomials in n variables. And you're given black box access to some element of this vector space, to some polynomial. And we'd like to evaluate the linear functional at this polynomial. Okay, so how many queries do you need to do this? So as a trivial example of this problem, if the linear functional is just the one that sends every monomial to 1, then of course, evaluating phi at a polynomial f is just equal to the sum of all the coefficients of the monomials in f, which you can of course compute with one query, just by evaluating f at the all ones vector. And we show that in general, the number of queries you need in the black box setting is characterized by the wearing rank of some polynomial. And so in this polynomial, the coefficient of the monomial x to the alpha is given by the value of phi at x to the alpha times some multinomial coefficient. And so indeed, if you plug in the linear functional from the trivial example, the polynomial we get is just the dth power of the sum of the variables x1 through xn, which of course has wearing rank 1. So yes, you really just needed one query to do that problem. So for us, wearing rank is a complexity measure of linear functionals on the space of polynomials. And just an idea of the proof. So if we define G as this polynomial whose Waring rank we're interested in. For the upper bound, we use the simple fact that if G happens to be a dth power of a linear form with coefficients a1 through an, then phi evaluated at f is just equal to d factorial times f evaluated at this point a1 through an. And this just follows from a simple direct calculation. The lower bound is a little more interesting. So if you happen to query f at m points, q1 through qm, where m is strictly less than the Waring rank of G, then it turns out that there exists some other polynomial h that will agree with f at the points q1 through qm, but where the value of phi at f is not equal to the value of phi at h. And this follows from something called the apolarity lemma, which is a tool that's widely used in the context of Waring rank and related problems. Okay, so why would we care about this for algorithms? So here's a question asked by Yannis Kudis and Ryan Williams. So what you want is an algorithm that computes the sum of the coefficients of the square-free monomials of degree d in some polynomial given to you as a circuit. And here a square-free monomial is just one where each variable appears to the power of 0 or 1. And so this corresponds to the case where the linear functional is equal to 1 on all square-free degree d monomials and 0 on all other monomials. So then phi valued at f is just the sum of these coefficients. And by the lemma, the number of queries is equal to the Waring rank of the degree d elementary symmetric polynomial in n variables. And this just follows immediately. And so this is actually one of the very few cases, one of the few families of polynomials whose Waring rank is known exactly. So it was recently shown that the Waring rank of the degree d elementary symmetric polynomial in n variables is equal to n choose d over 2. And in fact, the upper bound is very simple and explicit. So you'll see here in this original question of Kudis and Williams, you wanted to do something in time better than n choose d poly n. And here I've shown that the Waring rank of this is theta of n choose d over 2. And it follows from the lemma and this upper bound on the rank of this polynomial that given black box access to a homogeneous degree d polynomial in n variables, you can compute this quantity, the sum of the coefficients of the square-free monomials, using about n choose d over 2 queries. And this is optimal in the black box setting. So now a real algorithmic application. So say we have a graph G on n vertices, and we'd like to count exactly the number of simple cycles of length d in the graph. So closed walks where no vertex is repeated twice. Now, the fastest known algorithm I'm aware of runs in time d to the big O of d times n to the 0.174 d. And the fastest polynomial space algorithm I'm aware of runs in time 2 to the d times n choose d over 2 poly n. So we can solve the problem as follows. I'll give a faster polynomial space algorithm right now. So let A sub G be the matrix whose ijth entry is equal to the variable xi. There's an edge from vertex vi in G to vertex vj. And we set this entry to be 0 otherwise. So we've associated to each vertex in the graph some variable, and we've constructed this matrix. And we now define f sub g as the trace of the dth power of this matrix. And after a short calculation, you can see that this is equal to the sum of over all the closed walks of length d in G of the products of the variables associated to the vertices along the walk. So it follows, so in particular, for every simple walk, we have a square-free monomial And so the sum of the coefficients of the square-free monomials in this polynomial is just equal to the number of simple cycles of length d. And by applying this corollary, we get an algorithm running in time n choose d over 2 poly n for this problem, and polynomial space even. So the algorithm is extremely simple, and this is the whole algorithm. So you just have to compute this simple linear combination of the value of evaluations of this polynomial f sub g. And this extends to other problems like counting simple paths of length d and even counting subgraphs of bounded tree width in a graph. Now, unfortunately, this problem of counting simple cycles of length d is sharp W1 hard, so it's believed that there is no parameterized algorithm for this problem, so no algorithm with runtime of the form f of d times poly n for some function f. So you might instead consider approximately counting simple cycles of length d. And this leads to our main algorithms. So the first one says that if you're given a degree d polynomial with non-negative coefficients as a black box, then you can approximately compute the sum of the coefficients of the square-free monomials in time 4.075 to the d times some polynomial in n and 1 over epsilon. So you're computing a 1 plus epsilon approximation of this quantity that we were interested in before. And as a consequence of this, we obtain an algorithm for approximately counting subgraphs of bounded tree width in time 4.075 to the d, polynomial in n, and 1 over epsilon. And at the time, this improved the best known algorithm, which was due to Alone et al., and ran in time 5.44 to the d times some polynomial in n and 1 over epsilon. But this was subsequently improved by work of Bjorklund et al. So the idea of this algorithm is to upper bound the Waring rank of some polynomial that's similar to the elementary symmetric polynomial of degree d and n variables. And I'll introduce one notion of similar right now that I think is very interesting. So first observe that if g contained a simple cycle of length d, then this polynomial was supported on a square-free monomial of degree d. Okay. And now suppose you had some linear functional that is just non-zero on all square-free monomials and 0 on all other monomials. So this is a relaxation of before when we were saying it has to be 1 on square-free monomials and 0 otherwise. If you had such a linear functional, then by randomly scaling the input to f and evaluating phi at this new polynomial, then you can test if f is supported on a square-free monomial, which is a very useful problem to be able to solve. So motivated by this and the earlier lemma, we define a n comma d as the minimum Waring rank of a homogeneous degree d polynomial in n variables that has the same support as the elementary symmetric polynomial of degree d in n variables. And here the support of a polynomial is just the set of monomials appearing with non-zero coefficient. And based on what I've just said, this gives upper bounds on possibly randomized decision algorithms for problems like deciding the existence of simple cycles in a graph. And in the paper, I define other quantities related to, for example, approximate counting problems. But I think the most interesting one is just the one I defined here. So it turns out that this is very closely related. This quantity is very closely related to some methods in parameterized algorithms. So for example, there's this color coding method of Alone, Euster, and Zwick. And this seems to be equivalent to the fact that you can bound this quantity by 5.44, which is 2e to the d times log n. There was a subsequent improvement to color coding, which can be translated as saying that this quantity is at most 4.32 to the d times log n. And there's this group algebra approach that's widely used in parameterized algorithms, which really is just saying that when you define this quantity over a field of characteristic 2, it can be bounded by 2 to the d. And so we show in this paper that this quantity an comma d is between 2 to the d minus 1 and the smaller of 6.75 to the d and 4.075 to the d times log n. So somewhat remarkably, this quantity is actually completely independent of n. So if you think back to the rank of the elementary symmetric polynomial, it was about n choose d over 2. And so it goes down quite a bit. And this quantity has some remarkable properties. So for example, you can bound it recursively. And in fact, it's this recursive property that gives the color coding bound, the 4.32 to the d log n bound, and the 4.075 to the d log n bound. But what's very cool to me is the fact that even a bound for like a particular values of n and d can be translated to give upper bounds for all values of n and d. So for example, if an comma 4 is at most 11 for some large value of n, then in general you can bound this by something less than 4 to the d times log n. So just to summarize this problem here, here's the definition of an comma d. And the question that I would like to know is, can you bound this by big O of 2 to the d? And the reason I'm interested in this is because this provides a path to obtaining a deterministic 2 to the d times poly n time algorithm for problems like deciding the existence of a simple cycle of length d in a graph, which is a major open problem in parameterized algorithms. And so, for example, the previous approach to do this that I am aware of would have been to de-randomize polynomial identity testing. I don't know that this problem I've stated here is any easier than that, or that it's true, of course, but it's pretty interesting to me. And there's sort of a somewhat similar situation happening here as with the exponent of matrix multiplication, where we have some specific family of polynomials and upper bounds on the rank of these polynomials gives algorithms for some problems. Yeah, so I think that's it. Thanks. Yep. So there's this footnote. So I was actually sweeping this fact under the rug that the coefficients should be non-negative, but yeah, there's, yeah. Yep. That's exactly what I call it, yeah. Yep. So for the approximate counting problem, you're interested in polynomials that have the same support as the elementary symmetric polynomial, and also the coefficients of all the non-zero monomials are like between like 1 minus epsilon and 1 plus epsilon. So yeah, it's, for approximate counting, that's important.
Any other questions?